Hello and welcome back to computer science. So we are looking at our next non-programming unit, and we continue to work our way up through the layers of a computer system. So we started with data representation when everything was just ones and zeros, and we kind of saw how computers represent information. Then we moved on to logic and gates and circuits to see how those ones and zeros represented by electrical signals actually flowed through the machine and were able to accomplish various tasks. For example, we looked at the adder circuit. And now we're going to look at computing components or some of the hardware of a computer. And again, as with the previous layers, we start to take the other stuff for granted. So we assume that the ones and zeros are there. We assume that the gates and circuits are there. And that's what's directing the hardware that we're about to discuss for a little bit. Okay. So what we have here is an old computer ad. And I know it's an old computer ad because it's advertising Windows 8. But it still drives home the larger point that we're going to discuss is there's all this hardware listed, all right? There's all these components, all right? And some of this may not mean anything to you, but it all relates to the performance or the qualities of the device sitting in front of you. So for example here, Intel Core 2 Duo, 2.66 gigahertz, 1066 megahertz, FSB, 6 megabyte cache, right? So might sound like gibberish, but all of that has meaning. All right, this is referring to the cycles or the speed of the processor. FSB is the front side bus, which sends information from memory to input-output devices to the processor. This 6 megabytes of cache is internal memory that's kind of built into the processor, so it's really quick. And it's used to kind of accelerate the speed at which the processor can do things by having easy access to a limited amount of memory. Here you've got information about the resolution of the computer screen. And I know we've talked about resolution in pixels. All right, so the higher the resolution, the more pixels, which are the individual points of light that are making up the pictures and images that you see on the screen. There's other stuff here about RAM, and we're going to talk about that in this set of notes, the difference between primary and secondary storage. There's stuff about DVD and different styles of DVD, wireless protocols, which is how things communicate, USB, which stands for Universal Serial Bus. But there's all sorts of different things that it's kind of talking about here. And we're going to go into some of this, all right? We're not going to totally geek out on hardware, but we are going to talk about some of this stuff. And we're going to focus more attention on different types of memory and things like that. All right, so let's get started. So first thing we're going to do is just make sure that you have some fluency when talking about different units of storage. All right, so if we think back to Unit 1, all right, we learned that there are 8 bits in a byte, and there are 2 to the 10th bytes in a kilobyte, all right? So again, everything's in terms of binary. So technically there are 1,024 bytes in a kilobyte, but a lot of times that just gets abbreviated to 1,000. There are 2 to the 20th bytes in a megabyte, which is 1,048,576, but a lot of times that just gets rounded down to 1,000,000 bytes. And again, there are 2 to the 30th bytes in a gigabyte, and again, that's roughly like 1 billion bytes. So everything technically is in binary, but a lot of times people just use the shorthand and say, oh, it's 1,000 bytes in a kilobyte. Technically 1024. Oh, it's 1,000,000 bytes in a megabyte. Technically 1,048,576. Oh, it's 1 billion bytes in a gigabyte. Technically it's 2 to the 30th. All right, so just kind of keeping that scale in mind. Now, let's talk about putting in perspective. What does this actually mean? All right, we can list these numbers, but what does that relate to? What's something that we can compare it to? So for a kilobyte, you can think of it as one small email is roughly 1 kilobyte. So if you're trying to get a handle on how large that actually is. All right. A digital image. And again, this depends a little bit on the resolution, but a digital image is roughly about 5 megabytes. The lower qualities are going to be smaller, the higher qualities could be bigger. That gives us sort of a rough estimate. And then a gigabyte, all right, you could think of the flash drives or a thumb drive that you might have or have used in the past. Those are roughly like 32 gigabytes. So that gives you a sense for how large that is. Also, like this video that you're currently watching, I don't know how long it's going to go, but my rough estimate would probably be this is going to be like a 2 or 3 gigabyte video by the time that it's all done. So again, all of those things just give you something in your experience to kind of relate in what that actual size is referring to. Now, one thing that you're going to need to be able to do with these is be able to convert between different sizes. All right, so up here at the top, we have 1 megabyte is 2 to the 20th bytes. That's what we just talked about. So I could rewrite 2 to the 20th as 2 to the 10 times 2 to the 10. And I already know that 2 to the 10 is really 1 kilobyte. So another way to think of a megabyte is 2 to the 20 bytes, or it's 2 to the 10 kilobytes, and 2 to the 10 is 1024. So this is probably the part that's most useful, is that 1 megabyte is really 1024 kilobytes. And I could do the same sort of thing for gigabytes. Technically, it's 2 to the 30th bytes. I could break that down as 2 to the 10 times 2 to the 20th. And I know that 2 to the 20th is really a megabyte. So a gigabyte is 2 to the 10 megabytes, or 1024 megabytes. And we're going to use these to kind of run through our conversions. And these are going to look a lot like the conversions that you probably did in chemistry. All right, so let's take a look at a quick example here. Alice has 600 megabytes of data. Bob has 2,000 megabytes of data. Will it all fit on Alice's 4 gigabyte thumb drive? All right, so one thing we could do is we could say, all right, altogether they have 26 megabytes of data, 2,000 plus 600. Pretty straightforward. And we can say, all right, well, we know that 1 gigabyte is the same as 1,024 megabytes, aka 2 to the 10th. So if we multiply these out, the units megabyte will cancel out. We're going to be left with 2,600 over 1024. And this is now going to be in terms of gigabytes because our megabytes canceled out. And that's going to leave us with a final answer of 2.54 gigabytes. So to answer our question, yes, it will fit. All right, but that's one skill you're going to need to be able to replicate, is converting between, kilobytes, megabytes, gigabytes, in kind of any order that I give those to you. So let's do one more of these. Actually, we'll do 2 more of these just to make sure that we're good on them. So Alice has 100 small images, each of which is 500 kilobytes. Exactly how much space is needed to store these images in megabytes? All right, so again, I have 100 images. Each image requires 500 kilobytes, which tells me in total, I have 50,000 kilobytes of data. All right, just 500 each. I've got 100 of them. That's 50,000 kilobytes. What is that in megabytes? Well, I know that 1 megabyte is 1,024 kilobytes. So again, if I multiply these out, the kilobytes will cancel each other out. I'll be left with 50,000 divided by 1024. And I get a final answer of 48.83 megabytes. All right. So again, just kind of going through and doing those conversions one by one by one. All right, your ghost hunting group, because who's not part of a ghost hunting group, is recording the sound inside of a haunted classroom for 20 hours as MP3 audio files. Exactly how much data will that be expressed in gigabytes? Assume each minute of sound is 1 megabyte of data. Well, if we're doing this for 20 hours, and the last time I checked, there were 60 minutes in an hour. So 20 hours, 60 minutes in an hour. That gives us 1,200 minutes of audio. Now, we're told that each minute is 1 megabyte of data. So if we have 1,200 minutes, we have 1,200 megabytes of data. And if we want to convert that to gigabytes, we just have to say to ourselves, okay, 1 gigabyte is the same as 1,024 megabytes. All right, and then again, the megabytes cancel out. We do 1,200 divided by 1,024. That's going to be in gigabytes. And we get our final answer of 1.17 gigabytes of data. All right, every time I say this, I think of Back to the Future, when it's like I don't remember how many gigawatts, but it's like you need that many gigawatts of electricity to travel through time. If you haven't seen Back to the Future, you have no idea what I'm talking about, and you should probably stop this video right now and watch Back to the Future. Not really, but like maybe a little bit. Yeah, probably a little bit. All right, continuing on. What's bigger than a gigabyte? If you answered nothing, you are wrong. The answer is a terabyte, which again is 2 to the 40th. All right, so our numbers just keep getting bigger. And again, these are the rough estimates. Technically, it's 2 to the 40th. All right, a petabyte is 1 step up. This is the rough estimate. Technically, it's 2 to the 50th. An exabyte is another 10 exponents up. Again, that's the rough estimate. That would be the actual value. So 1 terabyte is what you're basically seeing most hard drives now are in terms of terabytes. So instead of having like a 300 gigabyte hard drive, most hard drives these days are up in the terabyte range. So it's not unusual to see a 1 terabyte hard drive. And 10 terabytes would be enough for the printed collection at the U.S. Library of Congress, which is the biggest library in the United States. So you can store a lot of text with 10 terabytes of data. All right, a petabyte is enough to get 3.4 years of 24 hours a day, 7 days a week, high definition video. All right, that is roughly 1 terabyte. So it's a lot of video. Now, exabyte, what exactly is that? For right now, let's just say very large. But this is when you're starting to get in the realm of like YouTube's video collection. So if you were to take all of the video on YouTube, you're starting to get in the realm of exabytes. All right, it's probably more than 1 exabyte at this point. Maybe it's in the 5 to 10 range. I don't really know. But that's what you're talking about. I mean, if you think about every possible single video on YouTube, even these amazing videos that I'm making, and put them all together, then you're in that range of like exabyte storage. All right. So obviously it's a tremendous, huge amount of data that one person is never going to need for themselves, or likely never going to need for themselves. Who knows? But you're just talking about a massive, massive amount of information. So again, it's good to be familiar with these just to have a frame of reference for when these words are being thrown around and what they actually mean. And then over here on the right are just some of the prefix derivations if you're interested in that sort of stuff. So when we are measuring size, we're looking at things like kilobyte, megabyte, gigabyte, terabyte, petabyte. When we are talking about speed, we switch over to measures of frequency. All right, so again, this is just better understanding the terms that get thrown around when we talk about computer hardware. So a lot of times you'll see hertz, you'll see megahertz, you'll see gigahertz. Right? So hertz is referring to the, not the car rental, but the cycles per second. So when you see something in megahertz, it is millions of cycles per second. And when you see something in gigahertz, we're talking about billions of cycles per second. Right? Now, from that computer ad that was on the very first page there, we saw it was a 2.66 gigahertz Intel Core 2 Duo processor. So what does all this mean? All right, so the 2.66 gigahertz is a measure of how fast it executes instructions. So this processor is roughly doing 2.66 billion instructions per second, which seems like a lot, and it is a lot, but you have to remember that individual instructions are super, super simple. Even the most basic code that you write in Python might be, 10 or 12 different instructions. So any more complicated code that you write might be thousands or hundreds of thousands of instructions. So the fact that it can do 2.66 billion per second seems really good until you really grasp how many instructions need to happen to actually accomplish anything. Intel is just the processor type or the company that is making it. So not all processors are Intel. That's just one company that makes them. Another one is AMD. And then Core 2 Duo means that there are two processors. So that allows the chip to kind of be doing two things at once, so that while it's working on one piece, a different part of the chip can be working on a different problem, and that can increase the overall speed because you've got kind of two people working on the same problem or different problems, as the case may be. All right. But again, hertz are sort of our measurement for speed. So when you're seeing hertz, that's referring to the speed of whatever you're looking at. So we've got some of those basic terms around. Now let's talk about this idea of the stored programming concept. And we're actually going to look at this in a lot more detail when we do like assembly language. But this is going to give us sort of a starting point for that discussion on assembly. All right, so this picture here is what's called the von Neumann architecture. And it's very simplified, but at its heart, it sort of represents what happens in any computer, no matter how simple, no matter how complicated. So you have input devices that feed into the machine. You have a CPU, which is like your processor, all right, that's primarily broken down into a control unit and an arithmetic logic unit. We'll talk about both of those in a little bit. And then you have a memory unit. So this memory contains instructions, it contains data, but basically this processor will retrieve instructions, retrieve data from memory. It'll feed them back in. It'll perform whatever calculations it needs to perform. And then eventually it'll send things out to an output device. So are we hiding a lot of complexity? Obviously, we're hiding a lot of complexity. But at its heart, this is what every computer does. It takes an input. It produces output. It has a processing element. And that processing element interacts with memory to get instructions, to execute instructions, to save information, to retrieve information, and so on and so forth. All right, so we're going to take a look at these pieces in a little more detail, but this is sort of the overarching sort of picture. So again, CPU, a lot of times I'm just going to say CPU, but when I say CPU, I'm referring to the central processing unit. All right. It has the control unit, which is sort of the stage manager. And the stage manager's job is to coordinate the other components so that they operate when and how they should. The arithmetic logic unit, not surprisingly, does your arithmetic operations. So again, that's referring to things like plus, minus, multiplication, and division. And then instructions and data are both stored in a memory unit. All right, and that memory unit can mean RAM, it can mean secondary storage, but we're going to see that this is where the instructions and programs that are being executed are stored. Secondary storage might actually be more of an output device, but the point remains the same. All right, so input-output devices. A device through which data and programs from the outside world can enter the computer system. Can you name some? So I'm assuming you can. There's the obvious ones like a mouse or a keyboard, but those are certainly not the only input devices. With phones, we have touchscreens. You have things like game controllers, because again, a gaming system is pretty much just a big computer. A flash drive that you plug into a computer can be an input device. It can also be an output device, but it's an input device as well. And then there are the more high-tech, futuristic input devices. You know, they're trying to like put sensors on your head that can read brain activity, and that brain activity feeds into a computer that then allows you to control a, you know, synthetic arm or something like that. You know, so there's the basics, and then there's everything we're trying to do as we move forward to go into the future. Right? Output device is a device through which results are stored in the computer memory. A device through which results stored in the computer memory are made available outside the computer system. So again, can you name some? There's obvious ones like the screen. Printer is an output device. Like I said up above, a flash drive is both an input and an output device. Different robotic things, if you're controlling some sort of robotic arm or something like that, that could all be, and so on and so forth. All right. Basically, you know, things outside of the computer that are being made to display some result or perform some action that are being kind of driven by the computer system itself. All right, so again, all part of that von Neumann architecture that we just looked at. You've got the input that goes into the system does something with it, and then it sends it to the output device. And again, we're hiding a lot of detail here, but that's the general sort of framework. All right, now that input device is likely going to be interacting in some fashion with the CPU or the central processing unit. All right, and this is broken down to those two pieces that I already briefly mentioned. But the arithmetic logic unit, again, just to reiterate, performs multiplication, division, addition, subtraction, and compares values to one another. All right, so that refers to less than, greater than, equal to. So if you think about our if statements that we've been exploring and using in Python, all right, that's going to interact with the arithmetic logic unit because we're forcing a comparison. Does this variable equal this? Is it less than this? Is it greater than this? Is the color distance above 100? All right, all of that sort of stuff is taking advantage of the arithmetic logic unit to make those comparisons. And then again, the control unit is the one that coordinates the actions of the other components. All right, there's a lot going on inside of the computer, and all of that needs to happen in a specific order at a specific time for things to work correctly. All right, that's the job of the control unit. All right, let's talk about the memory then. All right, and we're going to spend a lot more time with this than probably anything else that we're talking about today. All right, so a memory. Memory is a collection of cells, each with a unique physical address. So we have the addresses, which are in binary, because everything in a computer is binary. And then we have the actual data that's being stored at that address. All right, so this column is just location addresses. It's not actually information. This right here is our actual data or the contents. So for example, the cell at address 111111110 contains this information. All right, so this is just the location. This is what's being stored at that location. Now, when it comes to memory, there's really just kind of two basic operations that need to happen. You need to be able to fetch, and you need to be able to store. All right. Fetch requires one piece of information, the address that you want to fetch. Store requires two pieces of information, the address and what you want to store. You can kind of think of these as parameters if we're tying it back to our programming. So the parameter for a fetch operation is the address, which basically says go to memory and bring back contents stored at address. And that address is whatever was sent to the fetch command. Now a store is pretty similar. All right, you're still going to go to memory and store the value, which again is a parameter, at the address. So when you're doing a fetch, you need to specify what you're fetching, and then you just go and get the data. When you're doing a store, you need to specify where it's being stored and what that value is. All right, but these are kind of the main two things that memory is responsible for. Now, a quick word about addresses. Just realize that how many bits you use to define your addresses is going to affect how many addresses you can have. So right now, this is an 8-bit address, which means we can have 2 to the 8th total addresses, aka 256, and those addresses would be from 0 to 2 to the 8th minus 1, aka 255. So we saw this back in Unit 1 when we were dealing with like what's the largest number you can represent, what's the smallest number you can represent. There are 256 different addresses, but those addresses are numbered from 0 to 255. Right? This would be considered our range of addresses. So just realize that in a computer, memory is kind of divided up into the address, which is the location, and then the data that's actually being stored at that location. All right, and without these addresses, we'd have no way of knowing what to retrieve. So the addressing scheme is really important when we're talking about interacting with memory. Now, just a quick kind of side question. What does the bit pattern 10101010 mean? I don't know if I actually said enough 10s there. This is the cool part, and this is the part that ties back to Unit 1, is it could be anything. All right, that was the big idea from Unit 1, is that everything is represented as 1s and 0s. All right, so when we look it up, we don't know what it is. It could be an ASCII code. It could be a binary number. It could be the red in a RGB pixel. It could be a program instruction telling the computer what it needs to do. All right, we don't know what it actually is. We just know it's that sequence, and it's up to the program to interpret it and act on it correctly. So for example, if you've ever opened up like a picture in like Notepad or something like that, and you get a bunch of gibberish, that's because Notepad is trying to interpret it as ASCII, and the codes actually relate to a color or a pixel or something like that. So you're getting this gibberish, and it's not that it's gibberish, it's that you're using the wrong program to read it. It'd be like trying to translate French with a Spanish dictionary. Not really going to work very well. Okay. So let's break it down between main memory and kind of secondary memory or secondary storage. So main memory. Currently running programs and their data are stored in main memory, which is also generally known as RAM, random access memory, or primary memory. So what are some traits of main memory or RAM? All right, main memory is fast. Right? Doesn't really have any moving parts, and we're going to see in a little bit why moving parts slow things down. So main memory is really fast. A downside is that it's volatile, all right? Which means that when power goes off, its contents are lost. So obviously, when you turn the power off, your hard drive doesn't completely disappear because your hard drive is not main memory. It uses a different type of storage. But something like RAM does disappear. That's a lot of times why they tell you to like, did you restart your computer? Did you unplug it? Did you do this? Did you do that? By unplugging it, you're clearing out the RAM, which may clear out any issue or troubleshooting that was going on there. Now, it's volatile, so that's one thing you have to be aware of. The other thing is it tends to be more expensive. So there's a cost for this extra speed that we're getting. So the fact that it's more expensive limits how much we're generally going to use. Then other types of storage, and that could include things like SSD, which is a solid state drive, a flash drive, so on and so forth. And then I kind of already said this with the fast part, but there are no moving parts. Everything is electronic, which is part of the reason it's faster. So typical size of main memory on a PC, again, I'm not saying that all PCs have this, but a lot of them will be in like the 16 gigabyte range. So whereas hard drives have got into, terabytes, you're not going to see RAM go much above 16, 32 gigabytes, that sort of range. Not that there can't be exceptions, but a lot of times you're going to see it more in the smaller range because it is much more expensive than like secondary or hard drive storage. All right, so that's main memory. Let's flip over to secondary storage. Why is it necessary to have secondary storages? We kind of already said this, but it's larger and non-volatile. All right, which basically means that when you're doing long-term storage, even if the power goes off, the contents are preserved. It'd be really, really unfortunate if every time the power went off, you lost all the information on your computer. Probably make it so the computers wouldn't be nearly as popular as they currently are. If every time your power went out, it was like, oh, well, there goes every file I ever created. Super unfortunate. So can you name some of these devices? Again, a flash drive or a thumb drive is an example of a secondary storage device. Your hard drive is a secondary storage device. DVDs and CDs, not that people really use them that much anymore, are secondary storage devices. SSD, which is a solid state drive, which is just another type of hard drive that uses different technology. Again, secondary storage devices. So we've got main memory, which is our RAM. It's a lot faster, but it disappears when the power goes off. And we've got secondary storage, which is a lot larger. We're going to see that it's slower, but it does maintain things even when the power is removed, which is obviously a pretty important trait. So let's take a closer look at secondary storage and specifically magnetic disk hard drives. All right, so yes, SSD drives are becoming more popular, but still the most prominent form of storage is probably the magnetic disk hard drive. Pretty much every computer in the school still has a magnetic disk hard drive. And more importantly to the modern world is a lot of the cloud storage. So if you think about Google Drive, you think about YouTube, things like that, all of those, because of the size of storage that they need, are still working on like magnetic disk systems. All right, so we're going to talk about how these magnetic disk systems work. We're going to analyze their speed, and we're going to see that there can be a pretty big range in like the best case scenario and the worst case scenario when you're looking at these. So first of all, you've got these different disks, right? And these disks are essentially magnetic platters that are divided up into blocks, all right? And these blocks are where you have your actual data. So don't bother writing down the actual ones and zeros that I'm writing down because I'm just making these up as I go. But basically, this is where you're storing your actual information. So the disk is made up of different tracks, which are the circles around here. Now, obviously, these circles are pretty spaced out just so that you can see, but in actuality, they're super, super close to each other. Those tracks get broken up into sectors, which are kind of like these slices that you're seeing here. And the actual data is this block of information made up of kind of the divisions between like your tracks and your sectors. So a track, let's just put it this way, is a ring of data. So it's the rings going around the platter or the disk. The sector is a piece of the track inside a wedge, or I'm going to call it a pizza slice because I think that's what it looks like. And then you have the actual block here, which is the data stored in the sector. All right, so this is what one little magnetic disk is broken up as. And then what we have in a hard drive is we have lots of these disks on a spindle. The spindle will rotate, so the disks move, and then there's this read-write head that will slide back and forth. All right, there's this little read-write head that slides back and forth, and it's able to read the information off the disk as it spins around and around and around and around. So these are what we call our platters or disks. So you can almost think of it as like a record if you, why am I trying to explain records to people that were born after 2000? But basically this spins around, you've got this read-write head that's moving back and forth. And as these spin, it's able to read the information off the track. And if it needs to move to a different track, this read-write head can just slide back and forth to align itself with the appropriate track that it needs. All right. So again, this arm here moves in, moves in and out to position over the desired track. So we normally think of computers as very like electrical gates, signals super fast. But the main memory, not the main memory, the secondary storage the hard drive of your computer is actually a mechanical device. All right, it's these spinning magnetic disks and this arm that reads the information off of those disks. All right, so with this, we kind of want to analyze how quick, how slow all of this is happening. And to do that, there's some terms that we're going to need to associate ourselves with. All right, so the first term is the seek time, which is the time to position the read write head over the desired track. Right. So again, we have our different tracks here. That read write head needs to move in and out to be able to get on the right track. Like if the information you need is up here, the head has to physically move to get to that location. And the time it takes to do that, we call the seek time. Next is the latency time, which is the time spent waiting for the start of the desired sector to rotate around to the read write head. All right, so you're trying to get some information on the disk. The information might be right here. There, you have to wait for that disk to rotate so that it actually gets under the read write head so that you can read what's happening. All right, and we call that time the latency time or the latency period. All right, so this one right here is more of the seek time. And then last but not least is just the transfer time, which is the time it takes to actually read whatever data you want. So it's the time for the desired sector to pass underneath the read write head. All right, and this is just so data can actually be read. Right, because reading the data, again, involves the disk rotating underneath that read write head. So there's the time for the head to get in the right position or to the right track. There's the time to spin the disk to the starting location. And then there's however much the disk has to spin to actually read the data that you're trying to get. Right? So what we're going to do, and this is one of the skills that you're going to need in this unit, is now walk through one of these problems and how you can use this information, the sectors per track, the tracks per surface, the rotation speed, the head motion, to figure out how long different things are going to take for the hard drive, for the disk, for whatever system you're using. All right, this right here is a 3.5 floppy disk, which don't really even exist anymore, but they're small and they work well for our first example here. All right, but again, make sure you're paying attention because this is one of the skills that you're going to have to be able to do in this unit on your homework on an eventual test. All right, now the first thing we need to do with any of these problems is figure out the length of time it takes for the disk to make a full rotation. So we know that it makes 300 rotations per minute. So we're going to use that information to find out how long it takes for a single rotation. All right, so that's the first step when doing one of these problems, is time for one full rotation. All right, and this is generally going to be in milliseconds. So we know that if it is one rotation, or sorry, 1 minute, gives us 300 rotations. And we know that there are 60 seconds. Whoops, why do I keep doing that? In 1 minute. And we should know, or hopefully we know, that there are 1,000 milliseconds in 1 second. So if we kind of go through here, the minutes cancel out, the seconds cancel out, and we're going to be left with milliseconds. And we effectively end up with 1, 2, 3, 4, 1, 2, 3, 4 over 300. And this is going to be in milliseconds. So when we actually do that division, we end up with 200 milliseconds. So this is the time for 1 rotation. All right, so a single rotation of our disk is going to take 200 milliseconds. Now, what we're going to do is we're going to look at the best case scenario, the worst case scenario, and then the average scenario. All right, so by best case, we mean fastest. All right, so this is going to be the fastest scenario. So the seek time, if we remember, is the time for the read-write head to slide over the right track. So in the best case scenario, that read-write head is already going to be on the proper track. So in the best case scenario, which again isn't going to happen all that often, but when it does happen, the seek time is 0 milliseconds, right? Because the read-write head is already on the right track. Right? Now, using a similar logic, latency, which again is measuring how long it takes for the disk to spin so that if your data is right here and you need it to get underneath the read-write head, how long does it take to get to that location? Again, in an ideal scenario, and this one might be even less realistic, but in an ideal scenario, that's going to take 0 milliseconds because the start of the sector is already under the read-write head. Now you might be saying to yourself, does that mean the transfer time is going to be 0 too? No, transfer time can't be 0 because that's the time it takes to actually read the information off the disk. So that's never going to be 0. What that's going to be is we know that there are 18 sectors per track. We know that it takes 200 milliseconds to go around the entire track, because to go around the entire track, you have to do a full rotation. So the time to read one sector is just going to be 1 over 18 times the 200 milliseconds, which means that in the end, it's going to take 11.1 milliseconds. All right, so in the best case scenario, it's going to take our disk or our floppy disk 11.1 milliseconds to read one sector. All right, so that's best case scenario. Seek and latency are 0. Transfer is just the number of sectors, 1 over the number of sectors times the time for a full rotation. Now let's take a look at the worst case scenario. All right, so another way of saying worst case scenario is that it's the slowest. Now we can use the same information from before. So it's still 200 milliseconds for 1 rotation. Now the seek time, this is where we have to move our read-write head to the correct track. Now there are 80 tracks. So in the worst case scenario, you're on the inner track and you have to go all the way to the outer track. All right, so like my super awesome disk here. All right, but imagine there were 80 of those. We're going from the inner track to the outer track. Those are hideous. Those should be circles, but I don't even know what they are. But you'd go all the way from the inner track to the outer track, or vice versa, going all the way from the outer track to the inner track. Now, to do that, if there are 80 tracks, that means you have to traverse 80 minus 1 tracks. Right? So if you're starting at 1 and you have to go to 80, that means you're going over 79 tracks. It's telling us that it takes 3 milliseconds to move 1 track. So we're basically doing 79 times 3 milliseconds, which means it's a combined time of 237 milliseconds. All right, and this is when we go from outermost to innermost, or vice versa, which just means the opposite. All right, so in the worst case scenario, we went from 0 milliseconds to 237 milliseconds. So that's a pretty big jump in time. Now, for the latency in the worst case scenario is if we're in the exact wrong spot, if we're just a little bit past the start of what we need, then we essentially might have to do a full rotation to get right back to where we need. Like if we're just one little bit past where we need to go, then we effectively might need to do a full rotation. And we already know that a full rotation takes 200 milliseconds. So again, best case was 0. Worst case, we're up to 200 milliseconds. So a pretty big degradation in our speed there. And then the transfer time, this part is nice, that never changes, all right? It doesn't matter whether it's the best case or the worst case, it still takes that same amount of time to read that sector. The best case and the worst case really just affects the seek and the latency, right? And then if we add all of these together, we get a combined time of 448.1 milliseconds. So from best to worst, there's a pretty wide gap. Now, as I kind of said, it's pretty unusual that you're going to end up in the best case scenario. It's also pretty unusual that you're going to end up in the worst case scenario. So something we want to know is what is the average time that this disk is going to take to retrieve your information. All right, and this sort of stuff is important to remember because a lot of times people get obsessed with their processor or their RAM or this or that. But a lot of times your computer is only as fast as its weakest link. And if your hard drive is taking forever to get the information, it's not going to matter that your processor is super fast. Your computer is still going to slow down whenever it has to access the hard drive. So it's, people tend to focus on one number or another number, but it's really all of these numbers kind of working in concert that are going to affect how quick your machine seems to move. Now, when we're talking about the average seek time, you have to remember you've got your tracks here, all right? And sometimes you're going to have to move pretty much the whole distance. Sometimes you're going to only have to move half of the distance. Sometimes you're going to be in the middle and you only have to go a little up. Sometimes you're going to be a little, you have to go in the middle down. Long story short is that when you look at all possibilities, it averages out to 1/3 of the tracks. So on average, you're going to move over 1/3 of the tracks. And we could mathematically prove it, but for right now, we're just going to take it on faith that on average, going through this process, you're going to move over 1/3 of the tracks. So if on average, on average, so if on average we move over 1/3 of the tracks and there are 80 tracks and it takes us 3 milliseconds to move a track, what that's going to tell us is that on average, we're going to spend 80 milliseconds on our seek time, right? Sometimes it'll be less, sometimes it'll be more, but it'll average out to 80 milliseconds. Now the latency, same kind of idea here. Sometimes you're going to be in the right spot and have to move hardly anything at all. Sometimes you're going to be in the wrong spot and have to move a full rotation. On average, you're going to have to move half a rotation on average. Right. And the reason these aren't the same is that the disks are only spinning in one direction, where the head can move, up or down. So that's why this one's only a third, where this one's a half. Now, again, if a single rotation takes 200 milliseconds, and on average, we're going to have to do half a rotation, that means on average, our latency is going to be 100 milliseconds. And then again, our transfer time never changes. So that stays 11.1 milliseconds. I mean, it does change based on your rotation speed, but it doesn't change when you're sticking with those same values. And then if we add these all together, we get 191.1 milliseconds. So yeah, let me just make sure I'm clear on that. It's not that this is always 11.1. Ours is 11.1 because of the rotation speed and the tracks per surface and stuff like that. All right. So again, the calculation that we did back on the best case scenario is what dictated that 11.1. Right. This isn't set in stone for all hard drives. It's a function of the 200 milliseconds that it takes for us to rotate and the fact that we have 18 sectors per track. All right, but you can see there is a big difference here between best case, which was 11.1, worst case, which was 448.1, and average, which is 191.1. So, just based on where your hard drive happens to be at a given moment, your computer might respond slower or faster, and there's really nothing you can do about it. It's just the nature of using a mechanical device to retrieve your information. But this is something you're going to be able, or you're going to need to be able to do. And we'll practice this again, but I will give you different values up here describing the system. And then you need to be able to calculate the best case, the worst case, and the average scenario when retrieving information from whatever system I specify. Last question, and this one doesn't deal with speed, but more storage. So using the same information, if I tell you the total disk capacity is 512 bytes per block, how much data is stored if you use both sides of the disk? All right, so if you use the top and the bottom of the disk and store different information on the top and the bottom, what is the total amount of information that can be stored on this disk? So this is going to be, more similar to the conversion problems we were doing earlier, but let's just say we wanted to find the capacity of one side. We could say, all right, well, there are 80 tracks and there are 18 sectors per track. And we know that each sector stores 512 bytes. So if we were to multiply those out, we would find out that, okay, in total, we're storing 737,280 bytes. And you might be saying to yourself, well, okay, but what is that actually? Well, if we divide this by 1024, all right, we can see that it's actually 720 kilobytes. Right? Now that's the capacity of one side. They told us it was double-sided. So the total capacity, which means we're counting both sides, would just be the 720 times 2, which means 1,440 kilobytes. Or again, if you divide this by 1024, you can say it's roughly 1.4 megabytes. All right, so again, using this information and this extra piece of information to answer a question about the total storage. Right? And a hard drive might be made up of several disks. So you've got several disks kind of on that spindle that we saw earlier, and all of those together make up the entire hard drive. So again, you've got multiple disks here. Each of these disks have information on it, and all of the disks together make up the hard drive. All right, so this right here is just kind of a quick look back in time to see how far we've come. All right, so this picture right here is from IBM in 1956, and the hard drive weighed 1 ton. So obviously that's pretty heavy, and it stored a massive 5 megabytes. So basically, from our discussion earlier, 1 image or song. So for a 2,000-pound hard drive, we could store 1 song. Not great, and a sign of how far we've come, you know. Today's hard drives store, 1 terabyte and up. Not that they can't store less than 1 terabyte, but a lot of them these days that you buy are going to start at 1 terabyte and just go up from there. Okay, so obviously we've come a long ways when it comes to storage and figuring out how to store things and so on and so forth. Now, hard drive is the primary secondary storage, but it's not the only secondary storage device that exists, right? CDs, DVDs, Blu-rays, all secondary storage, right? Now, it's the same idea. You've got a disk that's spinning and you've got a read-write head, but instead of reading like magnetics, changes in polarity, we're using a laser to read and write information stored on a disk. So what we do is the laser physically burns pits into the disk. So when you burn a CD, you're literally burning in little pockets. And those pockets might represent a 1, and the flat sections might represent zeros. All right. So the laser burns pits into the disk. And then we read how the light reflects off that surface. So the light's going to reflect differently, whether it's hitting a flat surface or whether it's hitting a pit. And by measuring that light, we're able to read the disk and get the information off of it. And when we burn a CD, we're literally kind of burning those pits in there to represent the information as 1s and 0s. All right. And again, it's just happening at a really, really small scale. If you look at a CD, it just looks like a flat, shiny feature. But there are literally lots of like little pits in there in circles around the disk that allow you to kind of figure that out, figure out whether they're 1s and 0s. All right. Same thing with a flash drive. Not the same thing with a flash drive. Flash drive is totally different. But a flash drive is all electronic, all right, and has no moving parts. So that makes it more similar to the solid state drives that some people are putting on their computers nowadays for their hard drives. All right, so they work without kind of the rotating disks and stuff. All right, but then they're slowed down because they're not wired in. They have to go through the USB port, so that kind of slows them down a little bit. So even though there's no moving parts, we lose some of the speed because of the port that we have to work through to communicate with everything. All right, so last little bit here, and then we're going to be done for the day, is just a final comparison of primary and secondary memory. So again, primary memory is our main memory or our RAM. And the main advantage of that is that it's fast, which means the main disadvantage here of secondary memory is that it tends to be slower. Now, one of the disadvantages of primary memory is that it's more expensive, which means it's harder to get a lot of it. Whereas one of the advantages of secondary memory is it tends to be cheaper, so it's a lot easier to have giant secondary memories. Again, a downside of primary memory is that it's volatile, which means if the power goes off, you're going to lose your information. The downside is here that it's non-volatile. The upside here is that it's non-volatile. You get to keep your information even if the power goes out. Generally, this is going to be a smaller amount of memory, again, because it's more expensive and just the ways that we use it. And this is where you're going to have your larger amounts of memory, and also just physically, like to have the hard drives and the disks and the hardware is going to take up more space than some of the pure electronic systems. But obviously, like a flash drive is pretty small, and that can have huge amounts of memory on it. But then again here, primary memory doesn't have any moving parts, no moving parts. And the secondary memory often has moving parts. Doesn't have to, again, flash drive, but a lot of the mediums, CDs, DVDs, hard drives, generally have a lot of moving parts, which can sometimes be problematic just because those moving parts can more easily break. I mean, you're talking about actual physical hardware, and things can go wrong there and cause it to break that way. All right, so again, just some final comparisons of the two of these. Again, as far as the types of calculations you're going to need to be able to do, it's mostly going to be the unit conversions that we did at the very start of the video, and it's going to be best case, worst case, average case scenario, looking at hard drives. Other than that, you just want to be generally familiar with some of the terms, some of the vocab, some of the ideas that we went over in this video. Again, we'll do practice on this in the next couple of classes, but this is sort of a heads up of what's going to be expected. All right. Hope this was helpful. And obviously, if you have any questions, just let me know. All right. Have a great day.